Hi, in this video I will be going over how to analyze surfaces with an RFEM. I'll be using a concrete pipe as an example, and with the concrete pipe we'll be looking at how to divide up surfaces, analyze them, look at specific results, and determine whether your FE mesh is the right size or not for your model. So to start off, I'll go up here to the top left. I'll create a new model, and I'm going to name this model Video 8 Concrete Pipe. We're going to keep everything the same. Click OK. And now you'll see that our graphical windows popped up with our grid. The first thing I want to do for this model is I'm going to edit the grid spacing. So I'm going to go down here. I'm going to right click on grid, hit the edit button, and then you'll see this window pop up where you can edit your grid spacing and also the amount of grid points in each direction. I'm going to change my grid spacing to 1/2 foot. So now you can see that it's changed within the graphical window. I want to go up here and change my work plane. We're gonna set it to the XZ plane. And pretty much I'm going to just draw a line element, and this is going to be the center line for our concrete pipe. I'm going to make it 10 feet. Right click to cancel out of it, and now you can see we have our line along the global X direction. Now I can go up to this tool up here. You should have a drop down window where you can select which types of surfaces you want to create, and you can see we have a surface tool called pipe. This allows you to create a pipe super easy. The material we're going to set and go to import, and we want concrete, and we'll set it to the ACI standard, and then we'll set it to ACI 318, pick 4000 psi, and we want the thickness of our pipe to be 4 inches, and then we can set within this tab the radius of our pipe, and we'll set that to about 1 foot. Now you can see our cursor has a box next to it. That means we can select where we want to select which center line we want this pipe to be created on. We'll click the 10-foot one, right click and cancel out of that, and now you can see we have our pipe. So basically our pipe is made out of this one 2D surface just wrapped around that center line. You can see what this looks like and how it is defined just based on a wireframe view. And then we'll move on to how to divide this pipe into multiple surfaces for calculation purposes. So I'm going to drag from right to left. I'm going to highlight the pipe, and then I'm going to right click on it, go to surface, and go to split surface. You'll see that the split surface window pops up. It's taken our surface and it divided it based on 3 different cross sections, and you can see we have 4 different quadrants based on this. I'm going to keep all of this the same. You can see right here you can change your number of divisions for lines A and C and lines B and D. I'm going to click OK, and now you can see that those section lines have been applied and we have multiple surfaces defined. Now I'm going to go back and I want to add nodal supports to this left side, and I want to add a rigid surface to this right side so that we can apply our loads to it. So I'm going to change my work plane up here to the ZY plane. So we can easily just go up to new nodal support, and I'm going to keep this as hinged. Click OK, and now I can just rotate and I can drag from left to right, select those end nodes like so, and then I can delete this middle node nodal support. And now we want to apply a point load and moment load to the front of this pipe. So I'm going to change my work plane origin by going up to this tool up here, set origin of grid / work plane, and I'm going to set that to the center point. Now I want to create a rigid surface, a circular one, so I can go up to this tool up here, hit the drop down button, hit circular, and right here we can set our stiffness to rigid. This creates an infinitely rigid surface. I'm going to click OK, And now we can apply that to the end of our pipe. And there you go. And now you can see that our rigid surface is this pink color, and you can see that it differs from the gray color of our concrete. And now I want to add those point loads and moment loads. So I'm going to go up here and click on point load. We haven't created a load case yet, so it's asking us to create, I'm going to create a dead load case and just turn active self-weight off with this checkbox. I'm going to click OK. And then automatically our new nodal load window will pop up. And I want this nodal load or point load to be pulling the pipe in tension, so I'm going to set it to the positive X direction. I'm going to make that 30 kips. And then I want a moment force or torsional force at the end of our pipe about the X axis. So I'll set that to 15 kip feet. I'll click OK. And now you can see we have a little icon next to our cursor, and I click on this last node on our rigid surface. And now you see that our loading has been applied to the end of the pipe. Now that we have our loading and our supports added to our model, we can go up here and we can click Calculate All. Now you see that our global deformations are shown, and you might be wondering why our circular pipe looks more like a hexagon, and that is something I will get into a little bit later. The max global deformations that are shown on the pipe, and then over here we can change our results to surfaces, and this will show the basic internal forces such as moment about in the X direction and Y direction, shear, and axial forces. So before we get started looking at other results, I recommend going to Display, scrolling down to Results, going to Surfaces, and then we want to go into Distribution of Internal Forces / Stresses. And we want to switch this option from continuous within surfaces to constant on elements. And this setting ensures that the defined yield strength is displayed as a maximum in the result panel. So pretty much this gives you the yield strength for each element as you see on your surface, instead of averaging the results across multiple finite elements. So now we can move on to checking out the results. And right now we have our surface results turned on along with our basic internal forces. So I just really mostly want to concentrate on this one panel right here. To do that, I can go up here to this drop down and I can hit visibility by selected objects. And then over here I can turn on values on surface. And right now I just have my moments within the X axis direction turned on. So I want to go down to here and I want to have extreme values turned off. I more specifically want to have internal forces and stresses turned on right now. And then under stresses, under that subtree, we can turn on our sigma x and y on the positive side of the surface, our torsional forces on the positive xy side, and then along with our sigma x and sigma y on the negative side of the surface. We can also turn on our alpha sub m values. And that will give us the angle between the local x-axis and the principal axes. And then we can also turn on our max stresses from our von Mises calculation. And as you can see, those are displayed on our surface. We want to also make sure that our specific tree right here is checked on. So now you can see that with extreme values turned off and symbols and numbering turned on, we get these results at each of these points. And you can see that all of our stresses and torsional moments are shown. So now I want to move on, cancel out this visibility, turn off our results for a minute. And then I want to show you how to determine whether or not your finite element mesh is at the right length or not. So I'm going to highlight this whole model, and then I'm going to go up here to our move and copy tool, and I want to make a copy of this model and then move it 10 feet in the Y direction. What I'm going to do is add a finite element mesh to this whole entire model by highlighting the whole model, right-clicking, going to surface, and then going to FE mesh refinement, and we're going to hit new. Then we're going to create a new FE mesh refinement, and this one's going to be the entire surface. And we want the target FE length to be 0.2 feet. So we'll hit OK again. And now you'll see these little box symbols telling you that this surface has an FE mesh refinement on it. And then we can go up here and we can calculate our results again. Our results are generated, and now you can see how much finer and how much better our model with our smaller FE mesh looks for this. As you can see, we had a 1 foot FE mesh over on this model, and on this model we have a 0.2 foot FE mesh length on this model. And as you can see, that gives us a better accurate representation of our model with a finer FE mesh compared to the more blocky FE mesh over on this side. So now let's view the results. So once we go under values and surfaces and turn on specific results, we can compare the results between these two models and see how much they differ. I'm just going to select one of these panels again. So this is just a reminder when unsure about how large you should make your FE mesh. It all depends on the size of your model and the size of your surfaces. But if you change your FE mesh from one length to another and those results differ by a lot, then that means your FE mesh probably wasn't the right size. If you'd like to change the FE mesh of the entire model, you can always go up to Calculate, FE mesh settings, and you can change your FE length right here. And that'll change the FE length of the whole entire model. So I hope this video was helpful and was a great introduction on how surfaces work within RFEM. If you would like, you can check out our other short tutorial videos on our website or on our YouTube channel. Thank you.